All right, guys. Solving systems of equations. That's what we're going to be doing. First part of chapter 12. Chapter 12 really puts together a lot of things that we've done in the past, and kind of smashes it together with systems of equations and things. So it's really, I like the last, or one of the things we do in here, because it really takes everything that we've done up to this point and makes you use it. Okay. So if we're solving a system of equations, no matter what size it is, it can be a two-variable system of equations. It could be a three-variable system of equations. That's what we'll do mostly in here. It could be a 20-variable system of equations. Doesn't matter what size the system is, there are only three possible outcomes. One outcome is that it has one solution. That's called consistent and independent. We'll tie that together. One solution is consistent. That means it has answers. And independent means it's just one answer. Okay. The other option, or second option, would be that it's infinitely many solutions. That would be consistent. Consistent just means it has answers. And then it's dependent. Okay. Consistent and independent is one solution. Consistent and dependent is infinitely many solutions. So tie those words together. You may not have used those words in Algebra 2. I'm trying to build up a few things here and how this level starts talking about it a little bit more. And then the third option is the no solution option. And it's called inconsistent. So consistent means it has answers. Independent, one answer. Dependent, more than one answer. And then if it has no solutions, then it's called inconsistent. So tie those words together if you can. All right. So when we talk about systems of equations, if we're talking about two variable systems, so something like 2x plus y equals 5 and negative 4x plus 6y equals negative 2. There's a system of equations. What we're talking about here with that's a linear system because it has two variables. So you can put both of those in slope-intercept form, graph them, find out where they cross. That's the solution to that. That's one way of solving those. So we're finding out the intersection of the graphs with two variable systems. With three variable systems, we're looking at the intersection of planes, like flat planes out of that. So with these, there's several different ways that you learn to solve these over the years. We did graphing was one of them, and we did that in Algebra 1. I know. I think they do that in 8th and in junior high now as well. And then we learned substitution and elimination as options to do that. I mean, you could multiply the top one by positive 2, and you could get the x's to eliminate there with elimination if you wanted to, and then you get something for y, and then plug that back in, get x. We learned substitution. You could solve the first one for y and plug 5 minus 2x in the place of y right there and get x, get an equation just has an x in it. So that was another option that we learned how to solve that system of equations. And then when you got an Algebra 2 and we gave you a graphing calculator, we decided that we could teach you how to use a matrix to solve those. And y'all remember doing that in Algebra 2? All right, so the matrix that goes with this particular system would be what? 2, 1, 5, negative 4, 6, negative 2. What size is that matrix? 2 by 3. 2 rows, 3 columns. Okay, so we could put that into our calculator. Second, x inverse. We're going to go over to edit. And I don't have any matrices in there right now. Second, x inverse, which is right here.
Good morning, Dad. Please write for resolution.
All right. So going to our calculator there, second X inverse right there. To get to the matrix menu, press over to edit 2x3 matrix, and we're going to enter that one. 2, 1, 5, -4, 6. Okay. And then we're going back to matrix. We'll go to math, and we're using what? What did y'all use? Hopefully it was RREF. That RREF, and then we need to tell it what to use that on matrix A. And it cranks out a nice little matrix. Do RREF 1 0 2 0 1 2 or 0 1 1. Is that what y'all got? All right. So what's that mean? It means x equals 2 and y equals 1, or the ordered pair 2 1. This is what we're finding there. Is our solution for that. RREF, if somebody ever asks you, it stands for reduced row echelon form. There's this guy, or there's a couple of guys, and one of them was named Gauss, Gauss. The other one was named Jordan, like Michael Jordan, but not Michael. Completely different. But they developed this method with using matrices about the same time. So it's one of the rare cases where someone didn't claim, hey, I only want my name on it. They call it the Gauss-Jordan method. And you could go through a series of row operations to turn that first matrix into the last one and get there. It's kind of tedious and long way of getting there, but it does work. But the Gauss-Jordan method is what that is. And they called it reduced row echelon form is what they called it when they got to that last form where the ones and zeros on the left side and the answers are on the right. I'm that. I remember doing that in Algebra 2. All right, so let's do another one. So we had 2x plus 3y equals 1, and then negative x plus y equals -3. So our matrix would be 2, 3, 1, -1, 1, -3. And let's do the reduced row echelon form of that. So RREF on that one. So I'm going to use the same matrix again. I'm just going to edit matrix A because it's already the same size as what I need. 2, 3, 1, -1, 1, -3. And then here's the great thing about reusing that. Instead of having to hit all the buttons to get back to RREF and then pick the matrix, you can just press the up arrow and grab that command, hit enter, and it'll copy and paste it there. And now it's going to use the new matrix A that I put in there. It should does give me a different answer to -1 this time. 1, 0, 2, 0, 1, -1. So that tells us that x equals 2, y equals -1, or the ordered pair 2, -1. Yes, sir. Yeah, sure. So to get RREF, you're going to hit second X inverse to go to the matrix menu, press over to math, and the quickest way to get there is press the up arrow because it's down toward the bottom of that menu. Enter, and then you got to go pick up your matrix that you used. Crank it out. All right. So consistent and what? Dependent or independent? This system. Independent. One solution. Consistent and independent. And know the terminology that goes with it. All right. Example C. 2x plus y equals 5. And let's say we had 4x minus 8 equals negative 2y. What's different about this example compared to the previous one? Yeah, the x and the y are not on the same side in the second equation. So do they need to be? Yeah, if I'm going to use a matrix to solve this, they need to be. So all my variables need to be lined up kind of column-wise. So what are we going to do to get that to happen? Yeah, so you end up with 4x plus 2y equals 8. Yeah, no problem doing that in our head, I don't think. And so our matrix is going to be 2, 1, 5, 4, 2, 8. Okay. So I'm going to go back to the calculator, go to the matrix, edit. I'm just going to use that 2 by 3 that I've already got in there. 2, 1, 5, 4, 2, 8. And then I'm using RREF again. That one turned out different. I didn't get a 1, 0, and then a number like I did up here. I got 1, 1/2, and then a 0, and then I got, instead of getting a 0, 1, and then a number, I got a 0, 0, and then a 1. Okay? Anybody remember what that means? That means that there's no solution to this problem. Okay, so the matrix that we ended up here with 1, 1/2, 0, 0, 0, 1. That means there's no solution. And it's the reason we know it's no solution is that bottom row. What that bottom row says is that 0 equals 1. Does 0 ever equal 1? No, never does. So that bottom row, in no matter what size matrix you use, if we're dealing with a 2 by 3 or maybe a 3 by 4 in just a minute, or a 4 by 5, the bottom row can tell you what's going on. If it's all zeros and then a number in the very last column, then that's no solution. Okay, so that's important to know. All zeros and then a number in the very last column, that's no solution. Or it's also called what? Inconsistent. Okay, so those are the little higher level word, I guess, that we'll use in here. All right, so let's look at example D. Let's say we had 2x plus y is 4, negative 3y minus 6x equals negative 12. Oh, I'm sorry, that should be an x, the first one, sorry. 2x plus y equals 4. I think I said that and didn't write it. I wrote 2y. 2x plus y equals 4, and then the second one is negative 3y minus 6x equals negative 12. That is correct.
You have to get them lined up.
Do you? Yes. Yeah, absolutely. Right. So how do I rewrite? Let's just rewrite the second one, because we normally have x in the first column, y in the second column. So let's just rearrange the second one. Yeah, negative 6x minus 3y, negative 12. And then we have 2x plus y equals 4. Now we have a matrix that we can use. 2, 1, 4, negative 6, negative 3, negative 12. Through RREF, matrix. Edit. (214) -6, -3, -12. And then RREF again. And this one's even different from the last one we had. Look at the bottom row. Is it no solution? It's got 0 equals 0. Does 0 always equal 0? Yes. So that bottom row tells us that this is infinitely many solutions. Okay. 1, 1/2, 2, and 0, 0, 0. And that would tell us this is infinitely many solutions. And this is where we take it to the next level from what you did in Algebra 2, most likely. Algebra 2, you probably stopped there and said it's infinitely many solutions, didn't do anything else. Okay. What we're going to do is we're going to write the solutions in the form of one of the variables. Okay. So what we're going to do is we're going to look at that first row. Since it's the only other row we have, we're going to think about it as an equation. Is x plus 1/2 y equals 2. Okay. So what we can do is we can write that answer as a set of values, basically. So if we solved this this problem for x, we would subtract 1/2 y, right? X equals -1/2 y plus 2. So our equation, or our set of values, could be -1/2 y plus 2, comma, y. That's using y as your variable. You could also write it with x as a variable. And I'll specify on the quiz or test which one I want. So this one, it was easy to get x by itself, so that we wrote it as y in the first case. What if we took that same equation and tried to get y by itself? Subtract x, we'd have 1/2 y equals -x plus 2, and then we could multiply by 2, and y is -2x plus 4. So our ordered pair could be written as x is x, comma, -2x plus 4. Those are different ways to write the solutions. So it's infinitely many solutions. So if I picked an x value, I could find a y value that goes with it. That's what this tells me. This ordered pair notation here tells me. If I pick an x value of 2, I could plug 2 in here and get the y value that goes with it. But if I picked an x value that was -12 and plugged it in here, I'd get the y value that goes with it. I could generate an ordered pair that is a solution to this based on this infinite solution ordered pair. Same way here, but instead of picking x's, I'm picking y's. So if I needed to know, well, what's the solution when y is this? I'd say, oh, well, y is 5, then I'd plug it in here. And I could get the x value that goes with it. So this is kind of the next level thing that you probably didn't do in Algebra 2. You probably stopped at saying, oh, it's infinitely many solutions. Well, we're going to write those solutions in the form of one of the variables. We do x a lot, but sometimes y is easier. Sometimes z, when we do 3 variables, sometimes z is easier to do. But the bottom row of your matrix tells the tale. If it's all zeros, completely all zeros, we know it's infinitely many solutions. If it's all zeros except for the last number, the last one in the last column, then we know it's a no solution, which is the easiest of all ones to write the answer for. Not that any of them are hard. All right, so let's look at the 3 variable system. Say we had x plus y plus z equals -1, 4x minus 3y plus 2z equals 16. And when we have 2x minus 2y minus 3z, 5. What size is our matrix going to be? 3 by 4. Three rows, 1, 2, 3, 4 columns. First column is going to be your x's, second column is going to be your y's, third column is z's, fourth column is what the equation is equal to. So top row is 1, 1, 1, negative 1, 4, negative 3, 2, 16, 2, negative 2, negative 3, 5. Be careful putting these in. Easy to make a mistake. Miss a sign or something. Changes the whole thing. It's kind of like phone numbers. You miss one number, it calls somebody completely different. You probably don't even know the person you call. Guys, back up. That's supposed to be a minus z on the top. I didn't even copy the problem. Top row should be a minus z, so that makes it a negative 1 in that spot. Negative 1. Negative 1. There we go. Then we have 4, negative 3, 2, 16, 2, negative 2, negative 3, positive 5. Go back and make sure. 1, 4, 2, 1, negative 3, negative 2, negative 1, 2, negative 3, negative 1, 16, 5. Okay. All right. So there's our matrix. We're going to run RREF on that matrix again. I went ahead and did that in matrix A, so I didn't have to hunt back through to get my RREF. And there we crank out. What kind of system do we have here? What's it called? Is it consistent, inconsistent, dependent, independent? Is there an answer? Yeah, there's an answer because we've got ones and zeros on the left side. We got all numbers over here. The bottom row is not special. So we've got x is equal to 2, y is equal to negative 2, z is equal to 1. So we have a solution. One solution. So it's consistent and independent. X equals 2, y equals negative 2, z equals 1. Ordered triple, x, y, and z is the order that you would write that in. Again, that's consistent and independent on that. All right. There's example F. Another system, 2x plus y minus z equals negative 2. X plus 2y minus z equals negative 9. X minus 4y plus z equals 1. So set up your matrix for that. Get that put in there. Read that so you can still see it in case you didn't write it down. Hopefully you wrote it down. Get it. 2, 1, negative 2, 1, 2, 1, negative 4. So make sure you got your matrix in there. I usually enter them by rows because that's the direction your matrix goes. And then when I go back to check, I check by columns. So like 2, 1, 1 based on my equations, and then 1, 2, -4, and then -1, +1. And then the last column is -2, -9, +1. And that way, you kind of checked it in both directions. So maybe I catch a sign mistake. That tends to be the reason people miss these. You miss a sign when you're typing it in. Okay, so run your RREF on that. What do we know about this one? No solution. Why?
All zeros.
Zeros, and then it's equal to 1. 0 does not equal 1, so we know that's no solution. No solution. It's also called inconsistent. Those go together there. Out of that. Not too bad. Let's do the hardest part. One, I'm going to go ahead and tell you before we even start that it's infinite many solutions, and that's the hardest ones on the 3 variables is that because you got to write your solutions as a certain variable. Okay, so this is the most difficult part of that. So, example G. Here's our matrix: x minus 2y minus z equals 8. Then we have 2x minus 3y plus z equals 23. Then 4x minus 5y plus 5z equals 53. Put that into a matrix and run your RREF on that. You don't come up with all zeros on the bottom row, then something's went wrong. Run RREF. That. Is that what y'all got? Instead of 22 on the last column, 7, and then 0. So all zeros on the bottom row tells us that this is a consistent and dependent. Consistent and dependent system of equations. Okay, so that matrix, I'm going to go ahead and write it 1, 0, 5, 22, 0, 1, 3, 7. And then all zeros on the bottom row. So it's consistent and dependent. Okay. Infinitely many solutions is what we usually call that. Abbreviate that IMS, be fine. All right, so consistent and dependent. More collegiate way of saying that. All right, so let's write our answers in the form of Z. What that means is when you find X, it needs to be something with a Z in it. When you find Y, it needs to be something with a Z in it. Z is just going to be itself. That's kind of sometimes the easiest way to look at this is say, okay, well, Z is the one that I don't have any information about in my matrix, so I'm going to let Z stand on its own. Okay. So what you do is you take that matrix that you get after running RREF and you set it up as equations. You got X plus 5Z equals 22. And then you've got another equation. The second one is Y plus 3Z equals 7. Well, Z is equal to itself. That's the third equation you really have is that Z equals Z. All right. So if I'm going to get Y by itself, I just subtract 3Z. And Y is equal to -3Z plus 7. Pretty easy to get x by itself too, isn't it? So x is equal to negative 5z plus 22. So what you end up with is this set of values, like an ordered triple. In the x position, you're going to write negative 5z, z, plus 22. In the y position, you're going to write negative 3z plus 7. And in the z position, you're going to write a z. And that's your ordered triple. That if you picked a z value, you could find an x value and a y value that goes with it. Okay? All right. Questions about that? It's a little different. It's just an extra step from what you've done before. In the past, you stopped and said it's infinite many solutions, and that's it. Well, what kind of solutions are there? Going a little step further in the college level that we need to, hey, okay, that's what that is. Okay. All right. Let's look at an application that we can use systems of equations for. That was example G, so this is example H. Take 3 points from a quadratic function and create a function using systems of equations. All right. Now, 3 ordered pairs, -1, -4, 1, 6, and 3, 0. Okay. When we think about a quadratic function, we should be thinking about ax squared plus bx plus c. Those standard form for a quadratic. It knows way back chapter 6, right? No, what chapter 6? Chapter 3 we did some quadratic stuff, didn't we? Or chapter 4? Chapter 4 is what it was. Okay, so we got a standard quadratic equation there. Now, f of x is the same thing as what? Y. So what we really have here is an equation that has x's and y's and then variables a, b, and c. We don't know what a, b, and c are for the quadratic. So what we can do is we can create 3 equations with 3 variables in it using these 3 ordered pairs. Okay? So that's what we're going to do. This, and if you use quadratic regression with your calculator, this is similar to what it does. It's a little higher level calculation that it uses when you've got more than 3 ordered pairs, but it does something similar to this. So what we're going to do is we're going to use these x and y's here to do that. So for the ordered pair -1, -4, you can build this equation a times -1 squared, b times -1 plus c is equal to the y value, -4. And then for the next ordered pair, 1, 6, it'd be a times 1 squared, b times 1 plus c equals +6. And for the last ordered pair, 3, 0, be a times 3 squared, b times 3 plus c equals 0. That creates a system of equations. This turns into +1a minus 1b plus c equals -4. This one turns into 1a plus 1b plus c equals 6. The third equation turns into 9a plus 3b plus c equals 0. We've got a system of equations that has a, b, and c as the variables instead of x, y, and z. But we can solve it the same way. We can find the ordered triple, the a, b, and the c, using a system of equations. And the easiest way to do that is a matrix for that. So I would set up this matrix: 1, -1, 1, -4, 1, 1, 6, 9, 3, 1, 0. Set up that matrix, and RREF, reduced row echelon, for that. 1, -1, 1, 3/4. Nine, 3, 1. And so I've got this matrix set up here, and I'm going to run the RREF on it. And I get a nice little easy answer here. A is -2, B is 5, C is 3. Nothing really complicated about that. 0, -2, 0, 1, 0, 5, 0, 0, 1, 3. So our function would be -2x² plus 5x plus 3 is the function that contains those three ordered pairs. If you got all zeros and a 1 over here, what's that tell you about a function that contains those three? That one doesn't exist. There's no solution in the matrix, means that function doesn't, that quadratic function does not exist out of that. Okay. So there's a nice little application of three variable systems that we don't think about too much, but quadratics, building those based on that. Remember the name of that, what that's called. I can't remember it off the top of my head right now. All right, let's get just a couple other things here in this section that that you need to be able to do, and that's not necessarily using the calculator. It's using the thinker here. So let's look at that. So performing row operations. All right, so let's take example I. Here's our original matrix: 1, -2, +2, 0, 1, 3. Okay. Now, the performing row operations, when you do that RREF with your calculator to get the matrix into the reduced row echelon form, that's what your calculator is doing in the background. It's doing a ton of row operations to make things happen. What we want to be able to do is to do maybe 1 or 2 row operations on a matrix just ourselves and see what we end up with. I'm not necessarily going to make, I'm not going to make you by hand work one all the way down to reduced row echelon form. You used to have to do that. I don't see you gaining much out of that. If you take a linear algebra class, if anybody's going to be an engineer, you will take linear algebra, especially if you're going to be an electronics engineer or electrical. you'll take that course, and you get to do a ton of that fun stuff with that. So let's look at a row operation. Let's do this row operation. Row 1 equals 2, row 2 plus row 1. So we got to break out the notation. What's that even mean? Okay. Well, what it means is you're gonna change row 1 only. Row 2 may get used, but it doesn't change when you get the answer. Whatever it's equal to out here, that's the only row that's changing by that operation. And the operation they're saying to do is say 2 times the second row and add that to everything in the first row. Okay, and it's corresponding parts with that. So if I'm changing row 1, I'm going to take 2 times row 2, which is this one, and then add the individual part to row 1. Okay, so 2 times 0 is plus 1 is 1. So when I write my solution, I'm going to go ahead and copy down row 2 because it's not changing. Row 1 is the one that's changing. Okay, so 2 times 0 plus 1 is 1. 2 times 1 plus negative 2 is 0. And then 2 times 3 plus 2 is 8. And that's the completion of that row operation. Now, we ended up in reduced row echelon form out of that kind of on purpose, but that would have been the last step that your calculator would have done to get you there if you hit RREF with that particular matrix. Not always going to get there. Okay. So, following that row operations. Now, there will be times where they will give you more than one row operation to do, and they intend for you to do them in the order that they're listed. So let's look at that. Let's say here's our original matrix: 2, -4, 9, 5, 3, -7. And we're going to perform these 2 row operations. Row 1 changing by saying -3, row 2 plus row 1. And then row 2 changing by 5 times row 1 plus row 2. In that order. Okay, so this one happens after that one. Okay, so we got to get the answer to that one first before we can do that. So for the first one, what row is changing? The first one. So which one can I copy down? Bottom one. So 5, 3, -7. I know the second row is not changing yet. Okay. So then I'm going to look at it and say, okay, it says -3 times R2, which means -3 times every piece in row 2, and we're adding that to the row 1 value. So -3 times 5 plus 2, -13. -3 times 3 plus -4, -13 again. -3 times -7 plus 9 is 30. Okay. So that's after row operation number 1. Okay. Now for row operation number 2, copy down the first row because it's not changing. Row 2 is what's changing on that second operation. Okay, so I'm going to copy down -13, -13, 30. Now, it's 5 times row 1 plus row 2. All right, so 5 times -13. -65 plus 5 would be -60. Okay. And then we got a -65 plus 3, -62. negative 35, or no, negative 150 plus negative 7. It's not a negative, is it? No. 150 plus negative 7, which would be 143. And there is our matrix after we've done those two operations. Not necessarily that we're trying to go through row operations here to get to reduced row echelon form necessarily. We're just being able to follow the directions and do the row operations in a certain order. Kind of that. There are various kinds of row operations. Very rarely will you see them say minus, or row 1 minus row 2 or something like that. If they do, just do just that, that sort of thing. You can also swap rows. So if it said row 1 equals row 2, or there's a symbol that they can use like R1, and then arrows on both ends. That means swap those two rows. So, and that's legal to do in matrix algebra. This is one of my favorite classes in college was linear algebra. It was matrix stuff all the time. It was pretty cool. Maybe because we did a lot of stuff with the computer programming stuff, and that was in my wheelhouse, so it's easy. But anyway, row operations, follow them in order. So you'll have some on the homework assignments where you're actually trying to, they have 3 or 4 steps out of it. So just follow them in order, and make sure you only change the one that it says it's equal to. If you watch that, you're good. Okay. As far as the solving the systems, make sure you know the words. If it has one solution, what's it called? One solution would be consistent and independent. If it's got infinitely many solutions, it's consistent and dependent. And then no solution is inconsistent. Know those words out of that. Again, the hardest part is going to be writing your solutions for the infinitely many solutions ones, where you've got to put it in one particular variable on that. That's going to be the hardest part for you, I think, because it's really maybe the only new thing other than this row operation, and it's not very hard that you've encountered in this. So your assignment or problems on page 852, 17 through 79, and then 866, 5 through 87. Obviously the odds on that would be fine. That's not going to be anything just incredibly jaw dropping and stuff. So make sure you're